you're taking the Concise Physics textbook, the second chapter, the part that we have dealt with so far, work. Please do remember, whenever you are in doubt about what is there in the textbook, right, against what you must study in terms of the examination, please try to keep close track of the scope of the syllabus. Okay, so what is written over there is an indicator of what is it that is there in the textbook which is relevant to the syllabus, and therefore is something that you must study for your examination. There is a lot of other explanatory stuff which is also there in the textbook, but that is explanatory stuff and you don't really need to sort of commit it to memory or expect questions from those sections. So I'm just going to run through some of that for the work that we have done so far. Okay, so in terms of the first part of it, where they have given a definition or an explanation of what is work, this whole section is for reading. The blue box says work is said to be done only when the force applied on a body makes the body move. It's a kind of working definition of force. It's not the correct definition of force. You can just mark that section sort of as an working definition of what is force. And then it goes on to give some explanation about, like, an example of somebody pushing a car, an example of somebody pushing a wall. Obviously, what they are alluding to is that if the object does not move, then no work is done. And then we come to the section on measurement of work. So this part is, of course, important. Really speaking, your syllabus begins here, and then there is a sort of explanation for the magnitude of force and the displacement that is produced. The whole thing ends up with the equation. So this equation is something that is important for you to keep in mind. Now there is a mathematical definition, a statement made from this equation. The amount of work done by a force is equal to the product of the force and the displacement of the point of application of force in the direction of the force. Okay, it is something that can be used. I wouldn't use this definition. It can be changed slightly for it to sort of remove something that is unnecessary over there, which is they are talking about displacement as the point of application. So they are saying that it's not the displacement of the center of gravity of the object, but the displacement of the point of application. That may not be true in the cases. In fact, it is not quite correct to look at it like that, because there are also non-contact forces, and non-contact forces, there is no point of application. The point of application will have to be taken as the center of gravity of the object. So those who are having a closer look at that, you can appropriately tweak that definition. I don't think there should be any problem as far as the board is concerned. Then moving on, so they are giving you an example of a situation in which a force is applied and no movement happens, then what happens, etc., etc. And then the next part is this one, the one that we just discussed yesterday, in the second part of yesterday, that work is equal to F times S cos theta. Now, they have given some arguments for that. The arguments are for you to read. The derivation is not part of the syllabus. So, okay, so you don't need to really worry about the derivation part of it. We have derived it from the parallelogram law, which is, it's a more purer form of, if you can call it that, derivation, because it comes from trigonometric principles, it comes from understanding vector geometry, but they have done it in a slightly different way using an inclined plane, and the displacement that is caused along the inclined plane when you pull an object in a certain direction. You can look at that argument also. It works in exactly the same way. This approaches it from an application angle rather than from pure geometry, from pure vector geometry. So that is the difference, but again, the derivation is not part of the syllabus, strictly speaking. So I'm not expecting any questions. They haven't asked any questions in the last 4 or 5 years to derive the expression W is equal to Fs cos theta. So you don't have to worry about that. But though for those who are interested, you can work it out and you can make sure that you understand completely how this derivation works. And then there is a section upon by sort of, this is finding the component of a displacement along the force, one way of looking at it. Finding the component of force along the displacement. So this is the part that, this is the one that we have used, and this can also be used in the same way. Displacement being a vector, remember displacement is a vector. Distance is not a vector, but displacement is a vector. So therefore, you can also treat displacement as a vector and arrive at the same conclusion. The arguments will be the same as we used yesterday. And then we kind of, the whole thing happens, and then it gives you finally this part over here, which gives you a vector explanation. So actually, when we find out the vector product of force and displacement, what we do is we do what is known as a dot product. Okay, so in vector manipulation, you have a dot product and you have a cross product, and in this case we do the dot product. That is what is said over there. This is superfluous to the syllabus, it's extra work. If you are not interested in it, you don't need to look at that part. Just read it, read everything, but be clear that the kind of questions that you expect will be how do you calculate work done on an object when the force and displacement is given? Or it could be a force is applied on an object and the object does not move. What is the work done? I can't, and then of course numerical problems are possible, but in the numerical problems they can give you straightforward cases. A force is applied, a 10 Newton force is applied and the object gets displaced by a distance of 2 meters in the direction of the force. Calculate the work done. So then you can calculate it directly by just simply using W is equal to Fs. Now one question that I would like to talk about is, there are two equations, right? There is a work is equal to Ws over here, and there is a work is equal to, W is equal to Fs over here, and another one W is equal to Fs cos theta over here. So you may ask now, which equation do I use out of these two? Okay. If you are getting confused and you don't have a problem using trigonometric functions, then I say that every time use this, because you can always work out theta. You can say that if in the particular example that I gave, 10 Newton force causing 2 meter displacement in the direction of the force. So the question gives you the clue of what theta is. Theta is 0. So you can always write W is equal to force 10 newtons, displacement 2 meters, cos 0 degrees. So you will get 10 times 2 times 1, and therefore your answer will be 20. As of now, we write Newton meter, but we will come to what the actual unit is a little bit later. So I hope that is clear. Are there any questions that anybody would like to ask about this in terms of like understanding the textbook and its contents?